Okay, so in the previous lecture we were discussing about Euclidean domains, right? So let's continue our discussion on Euclidean domains. We had introduced the concept of a GCD, and in this lecture we will continue that discussion. So I guess in the previous lecture we had ended with this proposition that if A and B are coming from a commutative ring R, both are non-zero. And I want to have these elements such that the ideal generated by them, let me be writing them like this, and the ideal generated by them is a principal ideal generated by some element D, then I defined D to be the GCD of A. This is a very trivial proposition. What's important to observe here is that this is a necessary condition, not sufficient. This is a necessary condition, right? And an immediate counter example I would say to the sufficientness of this condition is that suppose I consider the ideal generated by 2 and x in Zx. Now previously we had observed that this is a proper ideal, right? This is a proper ideal, that is the ideal generated by 2 and x is not equal to Zx at any cost, but this is pretty easily observable that the GCD of 2 and x is 1, right? The GCD of 2 and x is 1, but the ideal generated by 2 and x is not equal to the ideal generated by 1, because the ideal generated by 1 is the whole ring Zx. I guess this part is clear, right? Okay. Yeah, let's define an important domain which is also quite sort of relatable. So an integral domain in which every ideal generated by two elements is a principal ideal, is called a Bezout domain. Recall what we studied as the Bezout lemma in elementary number theory. A quick recall will be simply that if you have two integers and you find their GCD to be D, then I can express D as a linear combination of those integers. That was what we call the Bezout domain, Bezout lemma, right? If you recall what we used to call the Bezout lemma, the Bezout lemma was that if GCD of two integers is D, then I can write D as a linear combination of these numbers, right? And exactly same thing is what we can generalize into a Bezout domain. So what does the Bezout domain primarily say? It says that an integral domain in which an ideal generated by two elements is precisely a principal ideal. Now the previous proposition simply says that since we are in an integral domain, so hence we are in a commutative ring. So in a commutative ring, if we have two non-zero elements such that the ideal generated by them is a principal ideal, then the generator of the principal ideal is simply its GCD. So this implies that D is the GCD of A and B, and moreover, since the ideal generated by A and B is equal to the ideal generated by the GCD, this simply means that D is contained in the ideal generated by A and B, which in other words simply speaks that D can be expressed as a linear combination, let's say A R plus B S, where R and S coming from R. So D can be expressed as a linear combination of A and B in R. So this is what we call an R linear combination. So D can be specifically expressed as a R linear combination of the elements A and B, okay, which primarily is exactly what it resembles in terms of the basolemma. Clear? And hence you can observe the why it's called a baso domain. Clear? And also it's quite observable from here that integers are baso domains as well. Moreover, this is a slight remark which I am just adding now, but we will prove it later. The proof is quite obvious, the structure in fact is quite obvious. The thing is that in UFDs, though the what we say, the Euclidean domains, sorry, the Euclidean domains, they carry over to the unique factorization domains, but unique factorization domain is not a baso domain. That is, if you have a GCD, you cannot express it in terms of as a R linear combination of the elements. Okay, so let it be for now. Let it be for now. We will talk about it later. Okay. Clear? Okay. The next theorem is what is actually a very important case, which actually shows that in integers we say that the GCD is unique, GCD of a pair of elements is unique or a number of elements is unique, but that is not exactly what happens in a general Euclidean domain. So the proposition, we will observe that why is it not that specific as it happens in an integers, but it's quite similar to that. Okay. So let R be an integral domain. Let R be an integral domain. Sorry, let R be an Euclidean domain, and let D be the GCD of A and B, and D dash is also a GCD of A and B in R. Okay. Or let me be proving a more general statement. I guess this will be a more general case. Okay. And suppose D and D dash generate the same principal ideal in R. Okay. Then D is equals to U times D dash, or you can say D dash is equals to U times D, whatever you feel like. That is, D is a unit multiple of D dash. Such elements are called associates. Such elements are called associates. This is a definition which I would be introducing while we start the discussions on unique factorization domains, but associates are basically unit multiples. So in this case we often say that the GCDs are unique up to associates, or you can also use the term the GCDs are unique up to units, because U is a unit. I have not mentioned it. Okay, sorry, where U is a unit. Where U is a unit. Clear? So in an arbitrary Euclidean domain, the GCDs are unique up to units or unique up to associates. Clear? So the proof. See, suppose D. So we are told that D and D dash are giving out the same, generating out the same principal ideal. So basically we have that the ideal generated by D is same as the ideal generated by D dash, but this implies that D is contained in the ideal generated by D dash, which implies I can write D as say D dash times R. While on the other hand, I can similarly express that D dash is contained in the ideal generated by D, which implies I can write D dash as D times S. So if I put this here, I'll get D is equals to DSR, or which implies D times 1 minus SR is equals to 0. Now this is an integral domain, since it's an Euclidean domain. So either D is a 0 or 1 minus SR is 0. Now D is a generator of an ideal. So typically we can assume it to be non-zero, because if it is 0, then there is nothing to prove actually. The 0 ideal is necessarily unique, right? There's nothing to talk about it, the generator of the 0 ideal being a unit multiple as such. So if D or D dash is 0, then it's typically a trivial case. So assuming D is not equal to 0 or D dash not equal to 0, so let just this be the case we start with. So this typically means that 1 minus SR is 0 or SR is equals to 1, but that means S is a unit or whatever, R is a unit, and we're done, right? Okay. What is the importance of this proposition which you can observe? It is that, as I said, that you know, the GCDs are unique up to associates, but I have not mentioned how can I say that. Observe that if D and D dash are both the GCDs of A and B, then this is something which we have obviously observed, that then AB equals the ideal generated by D and D dash, right? Or you can say it in this way as well, that D is the so recall the conditions which we had provided while we were talking about the definition of a GCD in terms of ideals, right? There we had shown that the ideal AB, it's typically contained in the ideal generated by D, and if D dash is another ideal which contains AB, then D dash must divide D, then the ideal generated by D must be contained in D dash. This is something which we had previously discussed, but this happens from either sides, right? This I can also replace it with D dash as well. So if I replace this with D dash, so yeah, so and if so suppose I make it D, then I'll have a reverse inclusion here. So in other words, which we can typically observe here is that the ideal generated by D is equals to the ideal generated by D dash, right? And hence D and D dash are units, sorry, associates. Clear? Okay, got it? I'm not yet speaking of the fact that if the GCD of A and B is D, then if the GCD of A and B is D, then the ideal generated by A and B is exactly equal to the ideal generated by D. That's not something I am talking about. Maybe I have miscommunicated the fact, but that's not what I meant. I meant this, exactly this statement. Clear? Okay. What more can I say? Now what we will prove is that indeed if I talk about a GCD in an Euclidean domain, then I can express a procedure in order to acquire that GCD, which is exactly similar to what we do in case of integers, where we follow the Euclid's division algorithm. So theorem, let R be an Euclidean domain and A and B be non-zero elements, which is quite precise start of the theorem. So let R be an Euclidean domain and let A and B be non-zero elements from R. Let D be is equals to Rn in the division algorithm, of A and B. Okay, then number 1, D is the GCD of A and B, that is the last divisor. So Rn, if you recall, Rn was the last divisor. If I let me just go back to where I started the discussion. So Rn was the last divisor, if you recall. Okay, so if we go back to the last divisor, then that indeed is the GCD of AB, last perfect divisor, I might think of it like that. Moreover, the ideal generated by D is exactly equal to the ideal generated by A and B, or this indeed what gives you the Bézout lemma, which I have already previously discussed. What the Bézout lemma is, indeed it typically what it says is that if I talk about integral domain, then it's basically a Bézout domain as well. Okay, it's a Bézout domain as well. Clear? Because if I am in an integral domain, then given two elements, specifically two non-zero elements, I can talk about a GCD between them, and in fact I can hence talk about them being a principal ideal. Clear? So proof. How do I try to prove this? So let me just firstly recall what was the Euclid's division algorithm as presented. So it was A being divided by B times, so A was equals to B times Q0 plus R0. Then we divided B by R0. So it was, I guess, R0 times Q1 plus R1. Then R0 was written as R1 times Q2 plus R2, and it continued, and every statement was some sort of this form: Rk minus 1 is equals to Rk times Qk plus 1 plus Rk plus 1, and eventually we reached a point where the remainder would become 0, and that was the nth point. So Rn minus 1 is equals to Rn into Qn plus 1. So I want to prove that this Rn is indeed the GCD. Okay, now how do I do that? See, AB is a, so since we are in an Euclidean domain, right? We are in an Euclidean domain. In an Euclidean domain, every ideal is a principal ideal. That's what something which we have already talked about. So the ideal generated by the two elements A and B, they are also principal ideals. So they are generated by some element, right? And now, so this is pretty easily observable, that which is following from the previous proposition, that if I take any two non-zero elements in some commutative ring and the ideal generated by both the elements is a principal ideal, then I can talk about the GCD of A and B being the generator of that principal ideal. So I already know about the existence of a GCD. Okay, so it just suffices to show that D is equals to Rn, right? We do not have to show the existence of a GCD. That's what I'm exactly talking about. I'm not writing this in statements. I guess you can follow what I'm saying. Okay, so how do I start? See, Rn divides, see, first point is that Rn divides Rn minus 1, which is observable from the last statement of the division algorithm, and Rn divides Rn itself, right? What I'm doing is that I am following a sort of induction. Okay, by induction, let Rn divide Rk and Rk plus 1. Okay, let Rn divide Rk and Rk plus 1. Now we have Rk minus 1 expressed as, so it was expressed as Rk times Qk plus 1 plus Rk plus 1, right? This, so since Rn divides Rk and Rk plus 1, this implies that Rn divides Rk minus 1 as well, and this happens for every integer. Now we, so therefore from induction it follows, therefore from induction it follows that Rn divides A and Rn divides B as well, right? Clear? So if Rn divides A and Rn divides B, then this typically means that A and B, this is contained in the ideal generated by Rn, right? Because A, so Rn divides A, that means that A is in the ideal generated by Rn. Rn divides B, that means that B is in the ideal generated by Rn. So any linear combination of A and B will be inside the ideal generated by Rn. And hence it typically follows from the fact that AB, the ideal generated by AB, is contained in the ideal generated by Rn, right? Now if I show the reverse conclusion, we are done. Sorry, reverse inclusion, we are done. Okay. So suppose or rather I can use the term, we know that I have written A as BQ0 plus R0, right? So this implies that R0 is contained in the ideal generated by A and B, right? Now B was equals to R0 times Q1 plus R1. This implies R1 is contained in the ideal generated by B and R0, but R0 was itself contained in the ideal generated by A and B, so this is contained inside the ideal generated by A and B. and I can exactly follow it inductively to say that Rn will be contained in the ideal generated by A and B. But this means the ideal generated by Rn is contained in the ideal generated by A and B. And so we have both sided inclusion, which means that the ideal generated by A and B is a principal ideal, which means that Rn is the GCD of A and B, and the second statement it readily follows from here only. Clear? Okay. Now this, all these propositions, this actually leads to a very fine number theoretic equation which are called the Diophantine equation, or in this case it's called the linear Diophantine equation. Linear Diophantine equation. So linear Diophantine equation is an equation of the form Ax plus by is equals to c, where a, b, c are integers, x and y are indeterminates. We need to find them. Okay. So if I take c to be the GCD of a and b, let's say, so this implies if I can express ax plus by to be the GCD of a and b, this is a linear Diophantine equation, right? And this is the statement which we have proved in the previous theorem. Hence this Diophantine equation typically has a solution. That's what I exactly want to say, right? In fact, the solution, so this has a solution, right? This has a solution in a Euclidean domain. You can talk about. Moreover, the solution to a Diophantine equation is typically not unique. Okay. If I consider this Diophantine equation only, then the solutions to the Diophantine equation readily are of the form x is equals to x naught plus some integer m times b upon the GCD of a and b, and y goes out to be y naught minus m times a upon the GCD of a and b, where m belongs to integers, and x naught, y naught are the already known solutions. So these are the solutions which we already know. So if we know some solution, then I can extend that solution to form the general set of solutions in case of a Diophantine equation. Okay. But how does this typically follow? So this is a very elementary number theoretic concept. You can easily check on both sides why this. So if you already have got a solution x naught, then you can check that x and y readily forms a solution to this equation. Moreover, if you can also restrict this to simple integers, and you can refer to any elementary number theoretic group, for like example, let's say Burton, you will get a brief, but I guess there was a detailed description. Yeah, you will get a detailed description of how this solution follows in the book of Burton on elementary number theory. What we are going to talk about now is its aspects in terms of algebra. Okay. See, if I talk about a first order or a linear Diophantine equation, say ax plus by is equals to n, then what I am actually asking is that, so this is equivalent to saying whether n is contained in the ideal generated by AB or not. But there is a well defined GCD of A and B, so I can also talk about the fact equivalently whether n is contained in the ideal generated by the GCD of AB or not. But then that is equivalent to saying whether D divides n or not, which typically means that this has a solution exists if and only if the GCD of A and B divides n. Clear? Got it? So this is sort of an existence of solutions in case of the linear Diophantine equations. Now let me introduce the concept of principal ideal domain, which we have already established while introducing the concept of an Euclidean domain. So let me quickly give the heading. Principal ideal domain. Okay. So as the definition suggests, an integral domain R is said to be a principal ideal domain if every ideal in R is a principal ideal. Okay. And we have already shown the fact that if R is an Euclidean domain, then every ideal is a principal ideal. Hence, an Euclidean domain readily implies a principal ideal domain, but the reverse conclusion is not true. Okay. The immediate example for the reverse conclusion to be not true is that the quadratic ring of integers z1 plus root minus 19 by 2, this whole by 2, this is a PID but not an Euclidean domain. We are not going to prove this. Proving this requires a lot of work, a lot of complicated work. So if in future I get some time to discuss specifically these examples which are quite complicated, then I'll do so. But for now you can consider this to be a fact. Okay. Some immediate observations you can also talk about is that, and which we have already seen also. Number one, that Z is a PID. It is readily proved by the structure of Z. Z root minus 5 is not a PID. We have already proved that, if you recall, that the ideal generated by 3 and 2 plus root minus 5 is not a principal ideal. Okay, but it's an ideal in Z root 5, Z root minus 5. Clear? So this is an example of a non-PID. Moreover, if you have two non-principal ideals, then their product can also be a principal ideal. That's a observation, or you can also talk about this being a remark. Let's say a remark, that is, suppose I take the non-principal ideal generated by 3 and 1 minus root minus 5, and I consider the other ideals a 3, 1 plus root minus 5, then this will give me just the ideal generated by 3. You can check it on your own. This readily comes from how the product of ideals is defined, which we have already defined in some previous lecture. So a product of ideals are specifically defined as finite sums of product of individual elements from each ideal. Okay. So therefore product of, so if you have two ideals which are not principal ideals, their product can still be a principal ideal. Okay. Moreover, since we have defined the concept of a greatest common divisor in an Euclidean domain, the definition still holds in a principal ideal domain, right? Because principal ideal domains are often induced by Euclidean domains, or if you start with an Euclidean domain, you will eventually reach a principal ideal domain. Therefore, if you are talking about a concept of the GCD in case of an Euclidean domain, you can also readily talk about that in a principal ideal domain, where the definition holds exactly the same. Okay. The most important aspect of defining the concept of a principal ideal domain is that, recall when we had discussed the concepts of prime ideals and maximal ideals, there we had discussed that the integral domain Z, that is the ring of integers, it is an ideal in which every non-zero prime ideal is a maximal ideal. If you recall that in Z, every non-zero prime ideal, or let me just mention it, the non-zero prime ideal is a maximal ideal. Maximal ideals are always prime ideals, that's quite precise, but every non-zero prime ideal was coming out to be the maximal ideal in case of the ring of integers. We will see that in case of a principal ideal, this holds in general. So theorem, or you can also state it as a proposition, that every non-zero prime ideal is a maximal ideal in a principal ideal domain. Proof. Okay. Let's dive into the proof of it. Okay. So what we do is that we start with a prime ideal, which is non-zero prime ideal, and we eventually show that it's indeed a maximal ideal. So let P be a prime ideal. Let P be a prime ideal. a non-zero prime ideal, that is P is a non-zero element indeed, P is a non-zero prime ideal, and we are talking about in a PID, so I am not mentioning that anymore. Let I be the ideal generated by M, be an ideal containing the ideal generated by P. Okay. So I need to show that this ideal I, it's either equal to the whole ring R or it's equal to the ideal generated by P. This will eventually show that the ideal generated by P is a maximal ideal, right? To show that I equals R, R is the PID in which we are talking about, or I is equal to the ideal generated by P. This will prove the fact that we are talking about a maximal ideal. Okay. Now suppose, so we have that ideal generated by P is inside the ideal generated by M. So what we have is that P is contained in the ideal generated by M, which means that M divides P, or we can equivalently write it like, say, P is equals to Rm, where R is an element from capital R. Okay. But if P is equals to Rm, this implies that Rm is contained in the ideal generated by P, or which means typically that so P is a prime ideal, right? So that typically means that R is in the ideal generated by P or M is in the ideal generated by P, right? Clear? So this implies that R is in the ideal generated by P or M is in the ideal generated by P. Now if M is in the ideal generated by P, if M is in the ideal generated by P, this implies that the ideal generated by M is contained in the ideal generated by P. This will prove the first part of the claim, that I is equals to the ideal generated by P. If not, then I have the ideal generated by R to be, or let me just write R to be PS, let's say, because R is in the ideal generated by P, but this implies that P, which was initially equals to Rm, it is exactly equals to PSM, which implies that P times 1 minus Sm is equals to 0. Now P is non-zero by assumption, and we are talking about in an integral domain, so this implies 1 minus Sm is equals to 0, or which implies that M is a unit. But if M is a unit, then the ideal generated by M must be the whole of R, which means I is equals to R. Okay. So what we have shown is that every non-zero prime ideal is a maximal ideal. So non-zero prime ideals and maximal ideals are equivalently spoken in case of a principal ideal domain, right? So this is a very fine case to talk about. The next observation, which will be the last thing to discuss in this case, in the next lecture onwards we will talk about unique factorization domains, and I'll also try to introduce a very specific sort of a norm which is called the Dedekind Hassse norm, which actually talks about or rather I can say it characterizes the existence of a PID. Okay. This I will talk about in the next lecture. In this lecture, what we are going to specifically talk about is this corollary. I think I can discuss the Dedekind Hassse norm in this lecture itself. Okay. Corollary: if R is a commutative ring such that Rx is a PID, then R is a field. Okay. This also holds in case of an ED as well. Okay. Proof. Okay. And the proof is quite simple. Observe that let Rx be a PID, let 0 not equal to x be an element from Rx, okay, or let me not talk about in this way because x is an indeterminate, so this is a very bogus statement to say that I am talking about 0 not equal to s. I can simply say that I can simply talk about the quotient ring Rx mod the ideal generated by x, where x is just the polynomial fx equals to x. We know that this is isomorphic to R, right? This sort of directly follows from the evaluation map at 0. Okay. Now this is a non-zero prime ideal. This is a non-zero prime ideal. Clear? This is very easily justified. So let me just use the statement justify. Okay. But observe that since x is a non-zero prime ideal, this means that this is a maximal ideal. This is a maximal ideal, right? This is a maximal ideal, but this means that Rx mod x is a field, which means that R is a field. Clear? Okay. Okay. So let me just end this lecture introducing the concept of a Dedekind Hasse norm, and that will be the end of this part. So the Dedekind Hasse norm definition: define n, or we define n to be a Dedekind Hasse norm if n is a positive norm and for all 0 not equal to a b in R, that is for all non-zero elements from R, either A is contained in the ideal generated by B, or there exists a non-zero element in the ideal generated by AB of norm strictly lesser than B, strictly lesser than the norm of B. How can I mathematically write this statement? That is either B divides A, or B divides A in R, or there exists element ST in R such that 0 is less than the norm of ST minus TB is less than the norm of B. Okay, this is what I am trying to state. Okay, sorry, SA minus TB, extremely sorry, SA minus TB. Okay, see, this is some sort of, you might think it of some sort of a generalization of the division in an Euclidean domain, because if you carefully observe that if I talk about R in let's say R is a Euclidean domain, then there exists Q and R in R such that I can write A as BQ plus R with R is equal to 0 or norm of R being less than norm of B, and since we are talking about a positive norm, so I can talk about this being greater than 0. Clear? The thing is that this exactly satisfies, or rather I can say this norm exactly satisfies the Dedekind Hasse norm, the condition for the Dedekind Hasse norm for S equals to 1. Clear? Do try and justify this out. Why this observation is important? Because the existence of a Dedekind Hasse norm, it exactly characterizes the existence of a PID proposition. Let R be an integral domain, then R is a PID if and only if R has a Dedekind Hasse norm. And this Dedekind Hasse norm is exactly the tool which we would require to show that the quadratic ring Z 1 plus root minus 19 by 2 is a PID. But that's still quite a very complicated set of statements, so we are going to avoid this for now. Proof of this statement is quite simple. Let I be a non-zero ideal of R, okay, and let B be a non-zero element of I, B be a non-zero element of I which now surely exists with norm of B being minimal, okay. Suppose A is a non-zero element from I such that the ideal generated by A and B is contained in I, okay. Then by the Dedekind Hasse condition on N, and the minimality of the norm of B, we have A is contained in the ideal generated by B, which implies that I is exactly the ideal generated by B, and this is principal, okay. So this proves that if I have a Dedekind Hasse norm defined on R, then I can say that R is a PID. The converse we are going to avoid for now. It requires some additional tools. Sorry, I shouldn't use the term cross, it would mean the converse is not true. Converse is avoided, but it's true. If you have a PID, then we can define a Dedekind Hasse norm on it. Anyway, it's sort of a tool which will be important, which might be important at least. Clear? So in the next lecture, we will introduce the notion of a unique factorization domain, and that will be the end of this part of discussing about integral domains. Later we will start with our discussion on polynomial rings, and we will specify certain integral domains on which we are defining the polynomial rings. For example, polynomial rings over unique factorization domains or polynomial rings over PIDs, okay. That will be a topic of some later discussion. So this is the end of the lecture. We will meet you guys in the next lecture.